Okay, right now, last time we have discussed about the Octo cycle, right? So we were in discussing about the gas power cycles, and there we first discussed about the ideal cycle like Carnot cycle. Then we move on to Octo cycle. Now, if you remember, now this is the PV diagram and the TS diagram for the Octo cycle. So if we start from one, we have isentropic compression process, right? Then constant volume heat addition process where the fuel is burned. Then isentropic expansion process, right? So isentropic means entropy is a constant. That's why this means S equal to C, entropy equal to constant. Then we have a constant volume heat rejection process, right? So that is the PV diagram. You know, when you compress it, increase the pressure, and the same time increase the temperature, right? In the TS diagram. Then constant volume heat addition process. Constant volume is constant, and heat, we're going to heat add heat. Therefore, pressure and the temperature increases, right? 2 to 3. And then isentropic expansion process, right? And therefore pressure and temperature reduce, right, decreases. And then lastly constant pressure heat rejection process, right? And the same thing we have mapped into the mechanical cycle as well as the thermodynamic cycle, if you remember, right? So then after we have derived equation for the efficiency neta, then we get neta is equal to 1 minus rk minus 1 over r k minus 1 r, right? So the r means, if you remember, the compression ratio, and k is a constant. Therefore we derive that the efficiency is depend only on the theoretically depend only on the compression ratio, right? Then we have discussed different compression ratios, and also we discussed different compression ratios for Octo engine, that means petrol engines, as well as the diesel engine, and how they differs, and how we can increase the efficiency, and why can't we increase efficiency further than 10, right? Normally in petrol engine we keep the compression ratio between 7 and 10, and also we discuss why we can't further increase the compression ratio, right? So those things have we already discussed. So what today's plan is to work on this question, right? So I think I have stopped in this place as I remember. So so we can work on this example. So I want you to pause the video and try to work on your own in this example, right? So I will be going forward. So let me work on the example. An ideal Octo cycle has a compression ratio of 8, that means R equal to 8. At the beginning of the compression process, air is at 100 kilopascal and 17 Celsius, and 800 of kilojoule of kilogram of heat is transferred to air during the constant volume heat addition process. According for the variation of specific heats of air and temperature, determine first one, the maximum temperature and pressure occurs during the cycle. So what is the maximum temperature and pressure, the network output, and the thermal efficiency, right? Now if we go back to this cycle and see, we know the maximum pressure occurs at 0.3, right? So the maximum temperature same as the maximum pressure, right? So we need to find this value, temperature and pressure, at 0.3. that is the first question. Then the network output, so we get the work output in here, right? Expansion, isentropic expansion, we get work output, and we have a work in 1 to 2 process, because it's isentropic compression. So compression work in, expansion work out. So we need to find the net amount of both the process, right? And here we have the heat addition, and in here we have the heat rejection, right? 2 to 3 heat addition, 4 to 1 heat rejection. So if we get that heat addition and heat rejection and also the network, we can find the neta value as well, right? Thermal efficiency, right? So that's the plan, and I have worked on this example, right? Now so this is how the system look like. So if we draw the things in a TS diagram, right? So it is given that R equal to 8, that means compression ratio, and we already know the P1, pressure 1 is 100 kilopascal, and the T1 also 300 Kelvin, right? So this point we know is given in the exam, given in the question. And Q in, that means Q in here, right? In here, the Q in here, right, is 800 kilojoule of kilogram, right? Those things we know. Right. So first part is determining the temperature and pressure at point 3, right? So we know temperature and pressure at point 1. So we can straight away go to point 3. We have to find these values in point 2, then we can go to point 3, right? So for that we can so let me start on the point 1. So we can refer the table to figure out the U1 value and the VR1 value, right? So there's a specific volume at point 1 and also the internal energy at point 1. So if we go to the property tables, right? So we are interested in looking into right, ideal gas properties of air, right? A17. Right. So our temperature is 300, right? Temperature is 300. Then so this is the row that we need to look into, and our internal energy 214.07, and specific volume is 621.2. So that is what is extracted from the table in here, right? These values. Then we can apply. So from 1 to 2 we know that the compression ratio is 8, and we also know V1 divided by V2. So V2 is smaller, V1 is bigger. Therefore V1 divided by V2 should be equal to 8, right? Because it's the compression ratio. Therefore we can derive this equation, right? V2 or V1 is equal to 8, and also therefore we can write VR2 divided by VR1, that means specific volume also should be, this ratio also should be 8, right? Therefore with that we can find VR2 comes like 310.6, right? So then we can look into this value, right? 310.6 in the table, right? So we are looking into specific volume, value is 310.6. So let's we go now. The specific volume is decreasing in this way, so therefore we need to look at 310, right, 0.6. So we should have value in between these two rows, right? We have 321 and we have 301. So what we can do, we can linearly interpolate find the value, right? So we can extract the temperature values and the the internal energy values. Then we can find what is the corresponding value, right? That is what is done in here, right? Then so we know the left one is T01 and the upper limit is 321.5, and then we can find the temperature, and also we can find the internal energy, right? Therefore first we have to find the fraction this fraction. So this fraction came to be 0.5452. Then with that we can find the temperature as well as the internal energy, right? Okay. So the temperature is after doing the calculation, temperature 395.48, right? And the internal energy is 282.893, right? So now we are okay with P2, sorry, U2 and T2, right? Then we can apply for the constant volume heat addition process from 2 to 3, right? It is given that constant volume heat addition is 800 kilojoule per kilogram. Therefore we can straight away find the U3 equal to 800 plus U2. So with that, if you substitute the value for that one, we get the U3 as 1082.893, right? Then we can figure out this value and U2 using U3 value from the table, and let's be right. So we are interested in figuring out the U3 value. Now U3 value is going all the way down, right? Now we are looking at 1082, right? 1082, right? Then so our value should be between this one, right? 1082. So our interesting value should be in between this one, right? These two rows, right? Therefore you can extract the temperature value 1340 and 1360, and also you can extract the U value, right? Sorry, U value, yes, we already know U value, right? 1058 and 1077. Then we can use those values to get the temperature, right? Then if we go back, so this is the U value, right? Okay. Yeah, interesting. So 1082 we are interested in. 1082 should be in this two, right? 1360 and 1380, right? Between these two, then therefore we can get this value 1077 and 1095. So that is the value in here, right? 1077 and 1095. Then our value, that means the U3, the one that we have calculated, should be in between. Therefore we can get the fraction as x. Then we can formulate this equation to find the correct fraction. The same way we can extract the temperature and specific volume values as well. Then using this fraction we can calculate the T3 and VR3, right? So once you do that, we get the T3 equal to 1363.6 Kelvin, right? We can later on we can find the VR3 as well, right? So for the moment we have figured out the temperature values, maximum temperature value, right? So the next thing is maximum pressure. Now we have completed the temperature values for 0.2 and 0.3. Then we had to figure out the pressure value for 0.2 and 0.3, right? So let's calculate the pressure value at 0.2. So we can apply the ideal gas law. Since at the both point, that means at the point 1 and point 2, we can apply PV equals to nRT equation, right? Then we can divide each other, so we can get something like this, right? Then with that one we can find the P2 value. We can get a P2 value here and Then if we apply the things, we can get the P2 equal to 1054.61, right? What I have done is apply PV equal nRT equation for point 1 and then point 2, then divide each other. Right? So n is cancel out because n is the same, therefore n cancel out. Then we are left with n and r, n and r both are cancel out. If we divide the things each other, then we left with this kind of equation. If we substitute the value, we can find P2 value, right? Then the same thing, same way we can apply. So for 2 to 3 process as well, if we find this thing, we will left with this equation. Right? With that we can figure out what is the P3 value as well, right? So this is the P3 value. So the first part is done. We have calculate what's the maximum temperature and maximum pressure of the process, right? So the next thing is network output. So the network output we can calculate U3 minus U4. This is the work output we get from the isentropic expansion process. So this should be plus because we get the work out is plus, right? Then we get minus work in. Work in is minus, therefore we get the minus. The work in is U3 minus U1. Right? So if we go back to here, right? So this is the work in 2 to 3, right? So this is the work in 1 to 2, right? Work in 1 to 2, right? The work out 3 to 4, right? That is what is in here, right? So that is yes, yeah, right here. Then we know all this value, right? We know this value. Then let me see. Do we know this value? We know U1, U2, and U3, right? U3. We are left to figure out U4 value, right? So for that one also we can formulate an equation using the compression ratio, right? So from process 3 to 4 we can get some value something like this, right? VR3 divided by VR4 is 1/8, but first we need to figure out what is VR3, right? So VR3 can be figured out from the above, right? We get it is right here. Okay, so we have the VR3 value here. From this part we can calculate the VR3, right? So we know the fraction is 0.81, right? From the, and we know the two limit values, right? Lower limit and the upper limit, right? Then using that one, this fraction, we can calculate what is the VR3. So that is what is done in here, right? 0.81 is the fraction, and we get that two limits, and we can find the VR3 value. So with that we can apply to this equation. Then we can figure out what is the VR4 value. VR4 value is 77.6 cubic meters per kilogram. So then we can use the table to find out what is this value. So we are interested in 77.6. We go back, so we are interested in VR 77 somewhere in here, 77, right? Our value should be in between this one, right? These two, 285 and 290, 285 and 290, that's 77. 285 and 290, right? So we are between 285 and 290, okay, right? 285 and 290. Then we can apply this equation. these values, u value and t value, and find the fraction as well, then we figure out the other two values, right? So we get the fraction equal to 0.675, then u4 equal to 492.02, and also later on we can find the t4 value as well if we needed, right? So since we know all the u values, u1, 2, 3 and 4, therefore we can apply to the equation A. So this is equation A. Then we can calculate the network output, right? The network output came as 522.05 kilojoule per kilogram. Then what is left is the neta value. Neta is equal to W net over Q in. So we know Q in U3 minus U2, right? That is constant volume heat addition process there, right? Okay, let me go back and see. So this is the constant volume heat addition process. So this is the Q in, this is the Q out, right? So we are not interested in Q out. So the Q in is the value we need, therefore U3 minus U2, Q in, right? So with that Q in, and also we know Q in is 800. This is given, right? You don't need to actually put the value here. You already know because it is given in the example details. And if we apply this value, we get 65% efficiency, right? So that is how we can work on this example. So the next video we will be discussing on diesel cycle.